Okay, so as I mentioned, there tends to be a little bit of tunnel vision when it comes to refrigerants. There tends to be this focus on GWP and more specifically in GWP being global warming potential of refrigerants. And it also tends to be predominantly in their in-use phase. So the phase where they're inside the equipment and being used. But there also tends to be this climate-only focus. So we're talking about the global warming impacts, but we're not necessarily addressing some of the other environmental aspects of refrigerants. So we'll talk about those a little bit today. So just so we're all on the same page, I think most of you are familiar with, let's say, the layout and how we define sort of embodied and upfront and whole life cycle carbon. Refrigerants obviously sit across those as well. So we have an upfront component, we have a downstream component. And most of the focus, as I said, tends to be on the operational side of things. The downstream side is obviously, sorry, the circular part is also very interesting. We perhaps don't have time to go into that today, but I'm happy to talk through how some of that fits into the picture as well. But we'll talk maybe sort of upstream, downstream today with a little bit on operational. Now, something I've sort of come across now and again is that by moving, say, from a high GWP refrigerant to a low GWP refrigerant, people maybe assume that there's already an automatic embodied reduction, but there isn't. There's a potential reduction, but it's not automatic. If we think of it this way, is in theory, if you've got a high GWP refrigerant in your chiller or your VRV system, if it doesn't leak, there's no impact at all. There's an impact from the way it's manufactured. There's an impact from the way it might be disposed of. But if you run a very, very tight system, there's no impact. And so it doesn't matter if you use high or low, there's effectively, there's no automatic win. But it just so happens that we're really bad at keeping this stuff contained. So there is certainly a need to move towards low GWP, but don't assume that it automatically provides an embodied win. Something that's interesting, if we just look at this slide here, because I noticed there was a release today about a GWP limit on small split systems, so 750 being the limit. But actually, if you look at the IPCC's latest data for R32, it's actually above that limit. So I'm not sure how that's going to sort of come into play, but it's a problem in a few jurisdictions when you use old GWP numbers. All right, so maybe just to highlight that point, if we had a VRV system, say with 8 kilograms of refrigerant in there, and it was leaking at 15% per year, which is something I've seen, it's not totally uncommon, and it might leak 18 kilograms over its life. And if we had another system that was only leaking at a very sort of small rate, maybe less than a kilo, then there's quite a big difference in their in-use emissions. It could be anything from, say, almost 14 tons to say 90 kg, which is still significant, but there's a big difference between the two. So if we look at, say, a life cycle example, so we can see in use, maybe it's between 92 and 14 tons. It's a big difference, which is why sort of leak mitigation is so important. But then, okay, what's the manufacturing and what's the disposal? Let's say the upstream, downstream, parts of that process. So this is where it gets interesting. So up front, if we're looking at how much, the footprint of our upstream process, trying to find accurate data is really, really difficult. Well, I'll be straight up, and I know that's the case across all types of, other services and components within the building. It's not just refrigerants that have that problem, but it's particularly tricky, and I'll explain why some of that is, and you'll start to see as we go along. So these are just a couple of sources from the open literature. So this is one from the International Institute of Refrigeration. So generally they're fairly credible, but they don't have a lot of information. This is it, and it's just a handful of refrigerants, and most of this data is from the 90s and the early 2000s. It's not particularly current. And then there's a policy advisory body in Brussels that put together a study just a couple of years ago. And you can see, again, if you look at R32 as a refrigerant, they've got 7 kilos over here, and yet in this study it's somewhere between 80 and 300. There's a big difference. So you start to question how reliable that data might be. And then when we come down to our low GWP refrigerants, our HFOs, there's not any, say, credible data available for that either. There's some mentioned over here, but the reason it's, let's say, questionable is because that was an industry-funded exercise. So we don't know where the boundaries were or how much was included in that particular process. And in the next couple of slides, you'll start to see perhaps why that is. So let's take manufacturing. We might have anywhere from, say, 7 to 200 and 300 kgs. Disposal, the downstream, is just as tricky. So this is a study taken out of Japan, and they've got the most sort of destruction capability, let's say, or number of units. Australia also has destruction capability. Average being about sort of 4 kg to destroy a kg of refrigerant, for example. I've seen some up to sort of 8 kgs, so say anywhere between 4 and 8. So this is what our life cycle starts to look at, and again, the in-use looks fairly high. And we could look at it this way. So in-use emissions look high, manufacture looks fairly low, as does disposal. But then you could also slice the data a different way, and you could say, well, if we take the high numbers for manufacture, if we've got a fairly leak-tight system, then actually the manufacturing emissions are perhaps the largest part of our complete life cycle there. So if we're talking about low GWP or lower GWP refrigerants, then that becomes an interesting question. I can see a few things in the chat. Would you like me to address those now, or sort of come back to them?
I was just interested, how do you destroy the refrigerants? Sorry, I just don't know what's the process.
Okay. There's quite a few different processes. So in Australia, they use what's called a plasma arc system, which is a very, very high temperature, high energy process, which destroys the refrigerants. You can also feed them into cement kilns and destroy them as part of, let's say, that combustion process, into municipal waste systems. There's a whole host of different ways, and there's some specific technologies for doing that. The one in Australia is quite interesting, and it was developed by the CSIRO. It's widely regarded as being the cleanest way to destroy refrigerants, but it's also uses a fair bit of energy as well. So that's maybe, say, one of the downsides. And my understanding is it's the intellectual property rights to that system has been bought over by a private company. So there's also maybe some restrictions about where that would be deployed. But in short, there's several ways to destroy it, and actually, I guess this is a point I'll come back to in the presentation, is all fluorinated refrigerants at some point will need to be destroyed, and that's kind of our challenge at the moment, is because we can't let them out to atmosphere, and even the low GWP have other impacts that we need to be aware of. So effectively, all of them are going to have to go through a destruction process at some point. That's the challenge we're facing. Question?
Yeah, hi there.
Yeah.
Thanks for running
Grace.
through this preso. Just want to clarify, with the manufacturing and disposal stage of the refrigerants, it is 295 kilograms CO2 per kilogram of refrigerant.
Yes.
And your in-use is the full emissions associated with about 15% leakage rate. So across 15 years, it's 14 tons CO2 emitted. That
could be the high end, yes. So it could be anywhere from 14 tons to, let's say 90, and then it could even be more than that. I'm just sort of taking a hypothetical scenario there. As you sort of can see, the leak management is still a really, really important area to focus on. But as we move into a low GWP refrigerant world, the upstream and downstream is going to become more prominent, put it that way.
Yep.
I guess that's the idea I'm trying to share.
Cool. Sorry, I'm just a little bit confused because the bottom right chart shows 295 under manufacture. Should it be 27,000 for 92 kilogram charge?
So 295 is taken from the top end of the manufacturing scale here. So
yeah, but wasn't that normalized by per kilogram refrigerant? Is that what you just said to me?
Yes, yeah. So this is let's say I'm taking the emissions at this stage, and this stage, and displaying them here. I guess the point being is that you can present that same data in different ways. So depending on whether you've got high in-use emissions or high manufacturing, it can let's say you can sell the refrigerant in different ways. That was perhaps the point I was trying to make.
I'm still a little bit
Still not
confused,
clear?
but let's move on. Sorry.
Okay. All right. Maybe if we've got time, we can perhaps loop back to that, or it might become clearer as we sort of step through. If we consider blends, so if you're not familiar, so blends are a mix of refrigerants. So some refrigerants are what we call single component, and some are blends where we combine two different refrigerants to get, let's say, the beneficial properties of both, so it becomes a compromise. One that we're starting to see sort of come into the industry for, say, chillers is this refrigerant called 513A. You could consider it maybe a lower GWP refrigerant with 573, and it's actually a mix of two other refrigerants, one which is a common one, and 1, 2, 3, 4, which is one of the newer low GWP refrigerants. Now,
I don't know if it's lagged, Adrian, but I'm still seeing R32 on the screen.
Oh, okay. Is anybody else, or is it just?
I'm still seeing the R32 slide as well. That's right.
Okay.
Yeah.
Same.
Okay. Apologies.
Can I just say, I think it may be that are you in presenter mode or something like that? That it's not.
Yes.
I think maybe that's what the thing is, that we're seeing presenter mode or something like that. And maybe it needs to be in a different mode or something. I'm not quite sure.
Okay. All right.
Just as a thinking could be. Sorry.
That's okay. Was it working okay up till then?
It was lagging a little bit.
Okay. It's the international connection. We'll try it again.
Yep.
Much lower emissions than flying you from France, dear boy.
Well, that's true. That's true. Okay. Can you see
now
it now?
we're seeing what about blends?
What about blends?
All right, good. What about blends? Okay. So this is what I was referring to before, is where we have this combination of refrigerants. Okay, and then what does that look like if we drill into those a little bit? And if we look at R134A, the production process, tell me if you can't see the screen come up here, but it's a bit like lifting the lid on a nested doll. If we really want to understand what goes into 134, and this is the process. So we've got everything from the raw hydrocarbons. So in this case, it's ethane, which comes through a refinery process. We've got fluorspar, which is the raw fluorine component. We've got sulfur, lime, brine. There's all sorts of stuff that goes into making a particular refrigerant, and a lot of people aren't familiar with this process. It's generally sort of out of view for most. But you can start to get an idea of just how much goes into making a fluorinated refrigerant. And then there's all the transportation. Often this is across different plants, different production facilities. So before it even gets to your customer site, it's gone through a whole stack of steps. And to be fair, that goes for lots of materials. It's not unique to refrigerants, but maybe people don't often quite appreciate how complex the refrigerant production process can be. And into that, of course, you've got lots of energy. You've got electricity, gas, water, steam, nitrogen, etc. Now, if we then look at one of the newer refrigerants like 1234YF, it's even harder. The reason being is that the newer refrigerants are heavily patent protected. So we don't know a lot about their production processes. We have some clues, but a lot of it is not in, let's say, openly available. I've taken this particular view. This is from one of the Japanese suppliers. They tend to be the most transparent, which is why I'm sort of using them as an example here, just to give you an idea of what sort of goes in and what comes out of a, let's say, a fluorinated production chain. So you can see some of those things we had before. We've got methane, we've got hydrofluoric acid, we've got some of the chlorine coming into this process. And this is where it gets interesting, because a lot of people perhaps wouldn't appreciate that a lot of fluorinated products are still made with HCFC-22. And if you're familiar with the industry, this is a ozone depleting substance that's being phased out for refrigerant use, but it's still heavily used for chemical feedstocks. And it just so happens that it's also used to make HFO-1234YF. Not in every case, but in some cases it's used to produce. So we're using ozone depleting old refrigerants to make new low GWP refrigerants. So it's not just refrigerants, there's also lots of other, fluorinated coatings. So even, for example, the insulation on your BMS control system cables in your structured cabling, that's probably gone through this process as well. Building, resins, all sorts of things. So it's interesting to look at it not just in the refrigerant space, or let's say the HVAC space, but also across some of the other materials. But the reason that R22 is still used here is because it has an exemption under the Montreal Protocol. It's not supposed to be emissive, as it shouldn't make it to atmosphere, but the problem is it still has some byproducts. And just to give you a scale, is actually, of all the refrigerant currently being produced in the world, most of it is actually for feedstock, so it's not for HVAC. It's actually for producing other fluorinated products, including refrigerants. But it's, this was data that's just been released, but actually, most of the refrigerant made in the world is for that purpose. And this is really the kicker. Sorry, go on.
Sorry, Adrian, just want to make sure we're seeing the right slide. I'm seeing the R1234YF production process.
Okay, you're still back here? Okay, sorry, it appears to be lagging. Okay. Okay. You're still on that same production process?
Still on that one, yeah.
Okay. Maybe we'll try it a different way.
I think, like Jeff said, if you do it not so much in
the
presenter mode, but just the normal slides mode, that sometimes helps.
I will do that. Okay. All right.
That looks more promising. Yeah.
Okay. All right.
Yes.
Yeah. Much better.
Yeah. Nice work. Well done.
Okay. I'll remember that for next time around. So yeah, I was just making the point that a lot of refrigerants is actually produced for chemical feedstocks. It's actually not for HVAC, which I think surprises a lot of people.
So sorry, Adrian, when it's produced for that, is it called refrigerant? Because it's not actually going to be used for refrigerant. It's used as a feedstock, like you said, for lots of other materials and things. Yeah,
it's a good point. Refrigerant kind of tends to get used because it's, let's say, a common name. So yeah, when people talk about R22, the R sort of designates it as a refrigerant. If we talk about HCFC-22, that's generally its use as a feedstock. So yeah, you in theory you wouldn't call it a refrigerant, but just because it's commonly known, that's the way it's used. It tends to sort of get dropped into that bracket. but you could call these, say, fluorinated greenhouse gases. That's perhaps the broader term that we use, or just F gases or FGHGs. Yeah, but yeah, that's a good question. But yeah, this is kind of the kicker, is that HCFC 22, when you produce it, it produces a byproduct called, well, HFC 23, and HFC 23 is one of the worst greenhouse gases. So it sticks around for 200 plus years. GWP, 14,000, and its concentrations keep rising, and most of that's associated with HCFC 22 production. So the reason I'm sort of looking at this or presenting this in the context of embodied carbon is because it depends where you want to stop. If you just want to look at HCFC 22, it's not so emissive because it's used in the feedstock production. But if you want to just extend the boundary a little bit to include HFC 23, then it changes the game. It changes the game in terms of what your refrigerant profile might look like. So this is a really key part of it, and which is why, for example, R22. I'll just bring up the pointer again. Yeah, that's why R22 here, is tends to quite high. Is if you include the HFC 23 emissions, it can be quite substantial. Now, that then begs the question: is if we've got a low GWP refrigerant over here, say 1234YF, which is produced by using HFC 22, is should we add the two together? And there's an argument to suggest that yes, we should, in which case it no longer becomes a low GWP refrigerant, potentially. So the thing is, of course, that there's different production paths, and not all of them use 22. Some of the newer plants in the US, they have a different process altogether. So then that really raises the question: is you kind of need to know where your refrigerant comes from. Which plant was it produced in, which country was it produced in, and which process was used to produce it. So at this point, I know I'm sort of raising more questions than maybe providing answers, but it's perhaps just to provide some context to where the challenges lie. And then if we look at the non-climate elements, I'm not an atmospheric chemist, so I'm not going to explain all this to you, but there's a lot happening when refrigerant gets released, and this is the one that tends to sort of come into a lot of conversations at the moment, which is TFA. TFA in many places is classed as a PFAS. It's a breakdown product from a lot of the fluorinated refrigerants, including the newer HFOs. It's not necessarily toxic at current levels, but it is persistent, and that's its problem, as it sticks around pretty much forever. And that's the concern, is it's really hard to get rid of, and it is accepted that is a breakdown product of the current refrigerant. So that becomes let's say, a chemical pollution problem. If we then look upstream at the manufacturing, the process does release toxic chemicals. That's the levels of the chemicals being released. That's not always easy to assess, but this is the list of common chemicals that are released as part of a HFC production process. Most of them aren't great for your health, I think it's fair to say. And then when we look at the disposal process, we've also got all these good things as well. Carbon monoxide is a big one for some of the incineration processes, acid gases, etc. As I mentioned, the plasma process is generally quite clean, but you've also got the energy input that goes into that process as well. Sorry, was there a question?
I was going to say, I didn't realize there was dioxins as part of it as well.
Yes, depending on the process. So if you're dropping it into a municipal waste disposal, and if you're not controlling the combustion process, you can release. There's a number of challenges with that process. It has to be carefully controlled. The challenge with fluorinated refrigerants is the thing that makes them good is the thing that also makes them difficult to get rid of, is because they're very stable. They have this chemical bond which makes them terrific you know, for use in coatings and refrigerants and all those things, but that bond is really hard to break down. So you need to throw a lot of energy at it to dispose of it. And, you know, in the process, you know, you can see all the chemicals that go into the process, you know. You know, some of that has to come through in the disposal side as well. So yeah, it's not just the GWP or the greenhouse gas part of the process. There's lots going on upstream and downstream as well. All right, and you know, just an example, you know, this is an EPD, I think from the Australia database. Yeah, there's this coating, you know, on this particular, you know, building material called Lumiflon, which you might recall was also on the AGC slide, so it comes through the HFC 22 route. But when you look at the EPD, there's no specific information on that, you know, on that particular pathway. So EPD isn't necessarily going to give you all the answers either. But we'll perhaps come back to that a little bit. And maybe just to sort of wrap up, you might be wondering if this is such a big problem. Australia's got disposal capabilities, you know, generally low tonnage, but if we look at it on a global scale, we've got about 6 million tonnes currently sitting in banks, and that's mainly refrigerant banks, but also foam banks. Refrigerants are also in the foams. And it's about, you know, let's say about a third of the world's, you know, annual emissions at the moment. It's a big bank. And if we were to say to use, this is like a plasma destruction facility, so there's one of these in Australia, for example, or two. If you were to run one of these units, if we were to stop producing refrigerants today, if we stopped right now, no more production, it would take 1,000 of these units running for 10 years just to destroy what's currently out there today. Yeah, and of course, you know, you look at all the predictions where we're not stopping today. In fact, it's going to increase. So the challenge of the cleanup is actually, I would argue, probably the biggest headache that we have. And you can think of that like a waste stream. So it's not necessarily, again, the climate or the ozone impact, is we just have a massive waste stream that we're going to have to deal with. So for me, that then sort of feeds into any decisions when we're deciding about what type of refrigerant to use, is to kind of begin with the end in mind, is think about, okay, this particular refrigerant that we're going to use in this system, what are we going to do with it at the end? Because something has to, you know, it has to go through some sort of end of life process. All right, so maybe I'll wrap it up there.